Welcome back. In this video, we'll be covering a lot of examples of analyzing and comparing functions with BigO, and then we'll be dividing those into families of functions and comparing the families for easier analysis moving forward. Recall that if some function is BigO of another function, then the first function will be less than or equal to the second function times whatever constant we want. These on the left are the functions that we'll be comparing. We'll start with x. So we want to know, is x big O of 1 or the other way around? So we'll just say, pretend x is f of x and 1 is g of x. Now this, if you recall the constant definition that we gave before, this is recognizably wrong. But if we want to just be sure, we can check. Now remember that if this is true, then 1 should always be on the top of our graph. Here's our graph, and x is on top. X is on top, so we know this is false, and actually we know that it's reversed. So if we just switch these, 1 is less than or equal to x, then this becomes true. 1 is less than or equal to x. Now we want to know where to place x squared. So we ask if x squared is larger than x. To do this, we can either graph it, or we can start algebraically and divide both sides by x. We get 1 is less than or equal to x, and this is true by what we did up here. So by this, we know that x squared is greater than x, and because it's greater than x, x is big O of x squared. We'll move on to x to the fourth. We want to know if x to the fourth is bigger than x squared. We can use the same trick here. We'll divide by x squared, and you get 1 is less than or equal to x. Once again, that is true, so x to the fourth is larger than x squared. What we have so far is 1 is big O of x is big O of x squared is big O of x to the fourth. This can also be written like this. 1 is less than or equal to x is less than or equal to x squared, etc. By this expansion, we see that 1 is also less than or equal to x to the fourth. So 1 is big O of x to the fourth, in addition to big O of x squared, in addition to big O of x. Generally, when we're dealing with asymptotic analysis, we want to find the tightest bound, but it's also true that 1 is big O of x and 1 is big O of x squared. Now we want to know if log base 2 of x is greater than x to the fourth. Just a side note here, generally in computer science we deal with log base 2, and so if you see log without a base in a computer science context, it's generally log base 2. The easiest way to evaluate this expression is simply to graph it. When we graph it, we see that x to the fourth shoots up really quickly, and log of x is way on the bottom. So we might even want to go to a smaller scale just so we can see it. When we do, we see that x to the fourth is most certainly larger. Back on our whiteboard, we said that x to the fourth was larger than log x, so we need to switch these. So log of x is less than x to the fourth. So where on this does it belong? Well, we can try x squared, we can try x, we can try 1, and we compare it until we find somewhere that it belongs. To save time, let's compare it to x. We see that x is larger than log x. We can go out farther and see that that's still true. So x is larger than log of x. As it turns out, log x is less than or equal to x raised to any positive power, no matter how small. So you can go down as far as you want, as long as k does not equal 0 and k is not less than 0. And we can see that if we tried to make k negative 1, we'd get a graph like this, and 1 over x is considerably smaller. Now we have a tricky question. Is log base 2 greater than, smaller than, or equal to log base 3? This one is easier to see algebraically. If you remember from your trigonometry class, you can change the base on logarithms. If we want to make this a base 3 logarithm, we can simply do log base 3 of x divided by log base 3 of 2. Now these expressions are equal. Log base 2 of x is equal to log base 3 of x divided by log base 3 of 2. And this works for any constant bases. So log base 2 of x can be converted to log base 3, it can be converted to log base 4, etc. As you can see, if we do that, this log base 3 of 2 is a constant value. There's no variable here. And in big O notation, as we mentioned previously, we ignore constants. So log base 2 of x is actually asymptotically equal to log base 3 of x. And that's true for log of any base. So natural log, which is log base e, we can also say is true for log base 2, log base 3, log base pi. Any constant value base will be asymptotically equivalent to any other logarithm base. So log base 2 and log base 3 are equal. On our equivalents here, we can see that 1 is big O of log base 2, log base 2 is big O of log base 3 because it's equal, log base 3 is big O of x is big O of x squared, and x squared is big O of x to the fourth. Carrying on, radical x, which is x raised to the 1/2 power. If we evaluate that against x, we can do this algebraically again. Divide by x to the 1/2 power. Whenever you divide, you subtract the exponents. 1 minus 1/2 is 1/2. So this will be 1 is less than or equal to radical x. And as we mentioned up here, this is x raised to any positive power. So this is true as well. And that means that x raised to the 1/2 is big O of x. As I mentioned earlier, logarithm is less than or equal to x raised to any positive power. This is 1/2 power, so logarithm is big O of radical x. So our radical x fits in right between log base 3 and x. We'll do x cubed next, just for simplicity's sake. X cubed will fit in this pattern of x raised to a positive power. We see that x to the 1/2 is less than x to the first is less than x to the second, and that pattern will continue on up for all values of k, all positive values of k. So x cubed is greater than x squared, but less than x to the fourth. So x cubed belongs right in between these two. I wrote our list here in order. 1 is the weakest equation. That's 1 is less than log is less than radical x is less than x, etc. And our strongest equation so far is x to the fourth. So that would be x to any constant power. It just keeps getting higher. Now, what we want to know is x factorial. Is that greater than x to any constant power? The easiest way is to graph this. When we graph it, we see that x factorial does grow much faster than x to the fourth. But what if we made x to the fourth a really high power? On this graph, it looks like x to the 100th just overtakes x factorial. But if we increase the range, we'll see that eventually x factorial gets much larger than x to the 100th. X factorial will always be larger than x to any constant. So x factorial is so far our largest. And now the question is x factorial big O of x to the x? Or is it the other way around? In other words, which equation is bigger? Which one is stronger? I like to look at this one algebraically. So x factorial is x times x minus 1 times x minus 2 times x minus 3 on down. On the other side, we have x times x on down. And on both sides, we have the same number of terms, because this will have x terms, this will have x terms. So the question is, which one is larger? Well, at this point, we can just start dividing things off. Divide by x, divide by x. You have 1 less x on both sides. We can divide by x minus 1. And the question here is x divided by x minus 1, which one is larger? X is, so this will be some value that's greater than 1, because x is larger than x minus 1. So this will be greater than 1, this will be greater than 1, but all of these will be reduced to 1. If all of these are equal to 1, 1 times 1 times 1, etc., is just 1. And we want to know if that's less than or equal to some value that's 1 times something greater than 1 times something greater than 1. What we do know from this is that this side will be at least 1. So we want to know, is 1 less than or equal to 1 or some value greater than 1? And that's true. So x factorial is less than x to the x. X factorial is big O of x to the x. We can look at this graphically. Here x to the x is in pink, and x factorial is in blue, and x to the x is growing more rapidly than x factorial. So to recap, we have our families of functions here. These are constants. Any constant number, 1, 2, 5, 100, pi, e. Those are all constants, and those will be less than or equal to any logarithmic function. So log base 2, log base 10, natural log, etc. And those are less than or equal to x raised to any positive power. So this can be however small, however large. Logarithm is always less than x raised to some power, some constant power. And if we're comparing x to some constant power to another x to some different constant power, then whichever constant power is bigger wins. Above that, we have x factorial. And above that, we have x to the x. These are our families of functions, and this is how we compare with big O. Next time, we'll be covering some more complex functions. Stay tuned. I'll see you next time.